In this part of the lecture, we're going to introduce some basic concepts about probability. What is probability? Probability is essentially the language to describe uncertainty. We use probability to quantify random events. A random process or a random experiment is a situation in which we know what possible outcomes could happen, but we don't know for sure which particular outcome will happen. There are many examples of random processes, such as coin tosses, die rolls, the stock market prices, just to name a few. We refer to the collection of all possible outcomes from a random process as a sample space. When we list the outcomes in a sample space, we need to make sure that these outcomes are exhaustive, namely, all possible outcomes have been included, and they are also mutually exclusive, namely, no two outcomes can overlap simultaneously. For example, the sample space of a single coin toss consists of two outcomes, head and tail. A die roll can have 6 outcomes, 1, 2, 3, 4, 5, and 6. In many circumstances, it can be helpful to model a process as a random event, even if it is not truly random. Think about the stock market. Each individual trade that's taken within the stock market is someone's particular choice about what they want to buy or sell a stock for. And that isn't really random. But with the system as a whole, it looks very random, and modeling it as a random can actually be extremely useful. Once we identify a random process and its corresponding sample space, which we denote as S, consisting of exhaustive and mutually exclusive outcomes, which we denote as, for example, O1, O2, and so on and so forth, then we can assign a number between 0 and 1 to each outcome, let's say OI, which we refer to as the probability or the chance for the outcome to occur. We denote it as P of OI, where P stands for probability. A higher value of POI means higher likelihood for outcome OI to occur. The probability 0 or 1 can be thought of as sure non-occurrence and sure occurrence respectively. Thus, we are going to require the sum of probabilities over all outcomes adds up to 1. This means that exactly one of these outcomes must occur, because by definition, all the outcomes are exhaustive and mutually exclusive. To define a probability distribution, one needs to specify a table listing all possible outcomes in the sample space and the corresponding probabilities. For example, when my wife became pregnant, we estimated that the gender of the baby could be either a boy or a girl, each with the probability 0.5. She had a friend who also got pregnant around the same time. So the genders of 2 babies have 4 possibilities. Both are boys, both are girls. Ours is a boy and there is a girl, and ours is a girl and there is a boy. Each one of these 4 outcomes will occur with equal likelihood, and hence with a probability 1 over 4. In history, there are 2 perspectives to interpret probability. The conventional approach is the frequentist interpretation, which views probability as the relative frequency of an outcome in a population. Therefore, the probability distribution is essentially the same as the relative frequency table we learned earlier. The frequentists believe that the probability exists and is objective. A more contemporary perspective is the Bayesian interpretation, which views probability as a person's belief about the likelihood of an outcome. Thus, for the same event, 2 different persons could have different probability assessments. Thus, probability does not exist and is subjective. This latter approach of interpreting probability in fact laid the theoretical foundation for some of the revolutionary advances in computational statistics for the last 2 decades. In order to work with probability, let's introduce some jargons that we will need. An event is a set of one or more outcomes in a sample space. Since the outcomes by definition are mutually exclusive, the probability of an event is simply the sum of the probabilities of the outcomes that constitute the event. For example, the probability of rolling a 1 or a 2 from a fair 6-faced die is simply equal to the probability of outcome 1 plus the probability of outcome 2, which is equal to 1 over 6 plus 1 over 6, which equals to 1/3. The probability of tossing a head or a tail from a fair coin is again equals to the probability of a head plus the probability of a tail, which equals to 0.5 plus 0.5 equals to 1. In this case, since the sample space consists of only these 2 outcomes, therefore their probability must add up to 1. 2 events are said to be disjoint or mutually exclusive if they cannot both happen at the same time. Namely, they cannot share common outcomes. Generalizing the examples above, when events are disjoint, the probability of one event or the others happening is simply the sum of the probabilities of each individual event. Now, let's look at an example. We call 2 disjoint and exhaustive events as complementary events. That is, complementary events cannot happen at the same time and they cover the entire sample space. We say one event is the complement of the other and sometimes denoted by using the superscript C. By definition of a complementary events, a simple but a very useful fact is that the probability of the complement of an event is equal to 1 minus the probability of that event itself. For example, boy and a girl are complementary outcomes. Therefore, the probability it is a baby girl can be computed as 1 minus the probability of a baby boy, which is equal to 1 minus 0.5 equals 0.5. Now, let's say a couple has 2 kids. What is the probability that they are not both girls?